Good day everyone, my name is Graphics. Today we want to solve a problem on stress and strain. Now if you look at the top right corner of the screen, you see a question there that says that a mild steel tie rod 3 meter long having a cross-sectional area 4 square centimeter is subjected to an axial pull of 1000 kilogram. If E, which is given as the Young modulus, for the steel is equals to 2 times 10 raised to the power of 6 kilogram per centimeter square. Find Roman figure 1, the stress, Roman figure 2, the strain, Roman figure 3, the elongation of the rod. Now when you see a question like this, the first thing you should do is write out your what? Your data. So the data given here, we have the D. The data given is DATA. We have a mouse steel rod. The length of the rod L is giving us 3 meter, right? And it have a cross-sectional area of 4 square centimeter, right? So the area A is giving us what? 4 centimeter square. Now is subjected to an axial pull of 1000 kilograms. So the force acting on it, we call it the P, or sometimes you can say the F, P, or you say the F, and that's giving us what? 1000 kilogram, right? Now, the next thing, we have the E for the Young modulus, which is giving us 2 times 10 raised to the power 6, 2 times 10 to the power of what? 6 kilogram per centimeter square. Now we're told to find the stress. We use this symbol for stress. We're told to find the stress. We should find the elongation, which is giving us what? There you call it change in L, or you call it your delta L, right? So, or you say it is E, giving us what? As what we're looking for. Now, the other one we'll talk about. So this is what we have: the stress, the strain, yes, and also the strain. Also, we're looking for the strain. Now, what you do is this: we are told that we should go calculate the stress. So the first thing we're calculating is stress. Now, calculating for stress, calculating, calculating for stress. Now we know that our stress is giving us what? The force P over what? The area, right? But if you look at this very well, cover that this is in centimeter, this is in centimeter. The Young modulus is given as a centimeter. So you have to convert your meter into centimeter. So how will you do that? You are going to what? Multiply by what? By 100. So converting meter to centimeter, you're going to multiply by 100. And in doing that, you're going to have 300 centimeter. Right? So 300 centimeter is equivalent to what? 3 meter. Now we're going to input our values into this equation here, this formula here. So we'll now say that stress here will now give us what is the force? The force is giving us 1000 kilogram. So we have 1000 all over the area, which is giving us what? 4, right? So 1000 over 4, and that is going to give us 250 kilogram per what? Centimeter square. So this is the answer to this guy. Now one thing you need to understand is this: says the length of a tie rod, right? The length, let's assume this is the tie rod here, this way, and the length of that tie rod is given as what? 3 meter, right? And it's related to what? An axial pull. So an axial pull, which is it is in tension, right? This is our force P, our force P. So in this kind of case, you're going to be expecting what? An increase in length. You're expecting what? An increase in length. So from here to here, it's giving us what? Our delta L, the elongation of the length. While here you are seeing is just called L, which is our original length. So now we've calculated the stress because the stress of on this bar here. Now we'll move forward. The next thing we are to calculate, if you look at the top right corner, to calculate for our strain. Now we know very well that calculating for strain, calculating for the strain, right, which is giving us this symbol here. So we know very well that our strain is giving us what? Is giving us change in length over what? Original length, right? This is one of them. But in our question here, we don't have our change in length and we also don't have our original length, right? So this is one relationship between strain, elongation, and length. I will just call it equation, let me say equation 2. Let me call this one here, maybe let me say 1, right? This formula here. Now, since there's no relationship between the strain here, we have unknown parameters, like we don't know two of them, right? Change in length and the strain. So the next formula we can think about is this. We know that our Young modulus E is equal to what? The stress over what? The strain, right? So what do you think we are going to use this? Because we have the stress, which is what we just calculated for. Then we have the Young modulus, which is what is giving us, is giving in our what? In our parameter. So in this way, we can now say from this equation here, we can say that the strain will be equals to what? The stress over the Young modulus. When I take the strain to this side and I bring the elongation, the Young modulus to this side, I'll be having this formula. Now, if you put your value, we say the stress here is given as what? 200 and what? 50. All over the Young modulus is given as what? 2 times 10 raised power 6. So we have 2 times 10 raised power what? 6. Now, if you do your calculation properly, the answer you're going to be getting will be 0.000125. Strain doesn't have units. It is dimensionless, right? So this is our answer for the strain. Or you can say 1.25 times 10 to the power what? Minus 4. Any of those two. Now this is our strain. Now the next thing we should calculate is, if you look at the top right corner, so we should calculate for what? Calculate for the elongation. So calculating for elongation, I'll call this equation 2 and I'll call this what? Equation 3. So we'll work with the equation 3 here, right? Now calculating for elongation. Calculating for the elongation, right? The elongation delta L is giving us from equation 1, we know that the strain is giving us what? Delta L over L, right? So from here, we can cross multiply. So our delta L, which is the elongation, change in length, will give us the strain times what? The length. I cross multiply. Now, what is the strain here? The strain calculated is 0.000125 multiplied by the length, which will have to be what? 300. So if you do that very well, now you are going to be having 0.0375 centimeter. So that will give us what? 0.0375 375 centimeter. Now this is the elongation of the rod. Now this is just a bar or a rod that has uniform cross section. That means the area from the beginning to the ending is the same, right? So if you found this video helpful, please don't forget to click on the subscribe button. Thanks for watching.